When you first get to your hotel, unlock it using your Magic Band bracelet. Hurry up and unpack your suitcase so that we can get into the parks right away. Make sure that you plan your outfits accordingly. The colors that you wear not only reflect your fashion taste, but these colors also reflect and absorb frequencies of light. A black t-shirt will absorb all primary colors of light, red, green, and blue. A white t-shirt will reflect all primary colors of light. Sunlight is energy generated through nuclear fusion in the sun. Light travels as a wave and particle, called a photon, at the speed of light, 3 × 10⁸ meters per second, to Earth just to shine on your t-shirt. When your shirt absorbs this light energy, it transfers into thermal energy. So a t-shirt that absorbs more light will be warmer. So the black t-shirt will be much warmer on a sunny Orlando day. These two shirts have the same basic design, but reflect color very differently. The white t-shirt still reflects all colors. The red t-shirt only reflects red, so it absorbs blue and green. That means it absorbs cyan light. Both of these t-shirts are blue, so they'll reflect blue and absorb red and green. They absorb yellow light. These blue shirts absorb their complementary color, yellow. The complementary color is always straight across the color wheel. These swim trunks appear green. That means they reflect green light. So they'll absorb red and blue or magenta light. In the deep end of the pool, however, these trunks might appear to be a different color. That's because water absorbs light in the order of the electromagnetic spectrum for visible light, or Roy G. Biv. Water starts by absorbing red and eventually absorbs all other colors. As you're unpacking, make sure to set aside your sunscreen. In the same way your clothes absorb light, your skin also absorbs those photons. Sunscreen blocks the ultraviolet light in sunlight that causes sunburns. If you want to be extra safe, you can also wear a hat. Now hurry up, we gotta catch our monorail. Look out the window and enjoy that beautiful blue sky. This is caused by the scattering of sunlight off the molecules and particles in our atmosphere. Scattering occurs when one of these molecules' resonance frequency is reached. Our atmosphere is made of small particles, so small wavelengths scatter, like blue. If our planet had medium particles, we'd have a green sky. If we had large particles, we'd have a red sky. Those happy white clouds are filled with water vapor. They appear white because they reflect white light, all of our primary colors. These clouds reflect red, green, and blue light. This means the light is reflecting off large, medium, and small particles. So white clouds are made of different sized water droplets. Along the monorail track, Disney recently built a solar panel array. You may have used a solar panel to power your calculator, but these power roller coasters. These panels apply the photoelectric effect to transfer the energy from a photon directly into electricity. As we enter Epcot, scan the RFID tag in your Magic Band and scan your finger in the biometric scanner. RFID stands for Radio Frequency Identification. Radio waves communicate between the RFID tag in your bracelet and the scanner at the gate. It communicated information linked to your Disney account. The biometric scanner uses infrared light to reflect off your fingerprint. It compares the reflected image to your fingerprint on file and confirms that it's you entering the park. Infrared light is naturally given off as heat. Let's set up a fast pass for our first ride, Spaceship Earth. Disney World lets you make this reservation on their app, so reservations are literally made at the speed of light. It takes our reservation 0.12 seconds to reach the communication satellite above. How far away is this satellite? Let's set up our givens. We know that we're dealing with the speed of light because it's a radio wave that's coming off our phone. We know the time, 0.12 seconds, and it's asking us to find the distance. I listed out my givens. That tells me my formula. Velocity equals distance over time. I plug in what I know, I solve for what I don't. What's happening to my distance? It's being divided by 0.12. So to undo that, I'm going to multiply both sides by 0.12. 36 million meters away. Your reservation is held because the RFID tag connects to your account. These radio waves that communicate with the RFID tag are perfect because they require the least amount of energy on the electromagnetic spectrum. No trip to Disney is complete without a character meeting with Mickey Mouse. Character meet and greet areas are designed specifically with photographs and selfies in mind. The lights in these areas are hung at specific distances and with specific intensities to make sure you look pretty. A light in the meet and greet area produces a luminous flux of 20,500 lumens and is placed 3.8 meters above Mickey Mouse. What is the illumination on Mickey? Let's start by listing out our givens. We know the luminous flux. We know the distance. We're asked to find the illuminance. Writing out your givens often writes out your equation. There's only one formula that has all three of those involved, and there it is. Substitute in what you know right underneath. 3.14 is pi. Simplify the top and the bottom. Remember to square and then divide to get your final answer. So Mickey's face is lit up with 113 lux. Before we leave the park, let's stop and grab lunch. Some of Disney's food is reheated at the restaurant in a microwave. These waves cause water molecules to resonate and generate heat. Now that lunch is done, let's hop on the Skyliner to head over to Hollywood Studios. The sky's lost its pretty blue that was caused by scattering. The white clouds, made of different sized particles, have been replaced by scary dark clouds. Objects appear black when they absorb light. Water absorbs light. These clouds are probably filled with rain. I really hope it doesn't rain. Of course, physics never lies. Let's hide out from the rain for a bit. Notice that the thunder followed the lightning, since sound moves slower than light. In fact, it moves 1,000,000 times slower. I just got an update. The park's closing its outdoor rides. Let's head inside to Disney's newest ride, Mickey and Minnie's Runaway Railroad. These Mickey and Minnie characters look amazing. They use projection mapping inside their animatronic faces to create fluid motions that make us feel like we're in a cartoon. They use projection mapping, which involves turning an irregular surface, like a building or a mouse's face, into a projectable screen. This ride uses projection mapping to project animated characters onto painted and lit sets. The projected images and lamps reflecting lights off the painted surface need to reflect with the same illuminance. If the illuminations are different, the ride isn't consistently believable or magical. That means we need to find the same illuminance with two different light sources from two different distances. The projector has an intensity of 40,000 candelas. It's animating a character on the wall 10 meters away. What's the illumination created by projecting the character on the wall? Well, we know the intensity. We know the distance. We need to know the illuminance. The formula writes itself. Plug in what you know and solve for what you don't. In this case, everything's over on the right. I'm going to simplify top, simplify the bottom, and just do order of operations. So I get 400 lux. The animated character has to reflect with 400 lux, just like the surface right next to it has to reflect with 400 lux. In order to create this illumination of 400 lux, a Disney Imagineer had to have placed a lamp 5 meters away. What is the intensity required to light the surface the same as the projector? So we know that our illumination is the same, 400 lux. We are looking at a 5-meter distance between the lamp and the surface. We need to find the intensity. When you write out your givens, the formula writes itself. There it is. I'm solving for intensity. I know illuminance. I know distance. So I need to simplify and then solve. I'm dividing by 25, so to undo that, I'm going to multiply both sides by 25. That means the intensity needs to be 10,000 candelas in that lamp. Otherwise, the surface will not be illuminated as much as the character next to it. It looks like the storm's cleared and the roller coasters are opening up again. So let's hop on the Seven Dwarfs mine train while the line is short. The ride combines an exciting roller coaster experience with state-of-the-art animatronic storytelling. The sound and light have to line up to tell the story. The challenge is that light and sound travel at very different speeds. So the light and sound are placed at different places. When you pass a dwarf, the speaker in your car plays a sound cue. If the speaker is 0.6 meters away from you, how long does the sound take to reach you? We know the speed of sound is 343. We know the distance is 0.6, and we're trying to find the amount of time. There's our formula. Substitute in. In this case, we can use our shortcut. Time is in the denominator, so we switch out 343. Throw that in our calculator, divide it straight out, we get 0.0017 seconds. Small amount of time, but it's a small distance. How far does the light emitting from the animatronic dwarf travel in the time it takes for the sound to reach you? We know the amount of time, and we know the speed of light. We want to find how far that light coming off the dwarf's face could travel. Formula always writes itself when you write out your givens. Be careful, when I type in speed of light, I need to use 3e8 in my calculator, or 3 times 10 to the 8th. When I plug this in, I have a one-step equation. I'm going to multiply both sides, and there's my final answer. If you struggle with your calculator, you can also type in 300 million, or 3 with 8 zeros for the speed of light.